integrated rate laws. Rate laws can be expressed to relate to the concentration of reactants to the time of reaction. Such expression is called integrated rate law because it is the integral of a differential rate law. Now, well, so far we have discussed the rate laws like this. The R is equal to K concentration of A. Concentration of A as we have here, raised to the power 1 for first order, raised to the power 2 for second order, right? Now we can introduce the rate of reaction equation and equate it to the rate law. Now this gives us a differential equation. And then we can integrate the differential equation. When we integrate this differential equation, we'll come and get this, right? Now, this relates the concentration to time. This relates the concentration at any time t to time. And this is what we call the integrated rate law. It is integrated because an integration of a differential equation, right? It's an integration of a differential equation. So this is the integrated rate law. Now, before any other thing, we have to keep this formula in our head. Very important formula. It will form the basis for all the other calculations that we will do. Very important. The formula is AT, that is amount at any time t is equal to A naught, which is the initial amount, exponential of KT. The K is the rate constant and the T is time. The T is time. Very important for us to take note of. So for first order reactions, we need this formula, as I've said. We can rearrange the formula. If we find natural log of this side, we can rearrange the formula to something like this. Now, this is a very important formula for us to know because it can help us draw a straight line to determine first order reactions. Now, if we represent the equation like this, if we rearrange the equation to this form, now the whole of this can be used to represent y. The mx here will be used to represent this one, the negative kt. The x here is the t, right? Now the b here can be the length of a naught, that is the intercept. And so what this one means is that if we plot the natural log, that's the length of AT versus time, we can produce a straight line with a negative log. So if this is our graph, this will be our straight line, right? Negative log, straight line like this, right? And so when we plot the length of the concentration at T versus time, and then we get a straight line with a negative slope, then it means that process is a first order reaction. What you have to keep at this point is, first of all, the equation for first order reaction. You can keep this one. The AT is equal to A naught exponential of negative KT. Or you can keep just this one, because this one can also solve all questions and then also help you in the graph. That's the length of AT is equal to negative KT plus length of A naught, right? So that is what we have had here. This is what I explained, that if you plot the length of A naught, AT versus T, you wield a straight line with a slope of negative KT, right? Now, this is a reaction. So consider the process of in which methyl isonitrile is converted to acetonitrile, right? How do we know this is a first order reaction? How do you know this is a first order reaction? Now, the first way that we used to determine the first order reaction was not in the integrated. It was in the differential rate law. And then that one, we had different experiments with the initial rates, and then we use inspection to deduce the rate order, the order of reaction. Now, when we give you the concentration and the time, you need to use graph to determine the rate of reaction. We'll first talk about how you can determine whether it's a first order reaction, and we'll talk about how you can determine whether it's a second order reaction. We'll come and talk about how you can determine whether it's a zero order reaction. So first order, how can we see that this is first order reaction? Now the data is being collected at 198.9. This is very important because K is constant at constant temperature. Temperature will change K, right? So how do we know? Now, if we just plot the concentration against time, we'll get a curve. The curve cannot really help us deduce anything, right? And so what we have to do is that we have to plot ln, right? Now, because it's a gas, we use the pressure instead of the concentration, the pressure of the methyl isonitrile versus the time. Now, if we produce a straight line with a negative slope like we have had here, like we've had in this instance, that means it's a first order reaction. It means it's a first order reaction. So that is what we have here. The ln of P is plotted as a function of time. The straight line results. The process is first order reaction. So this is a question. For the question is given the following rate data concerning the decomposition of sodium azide into nitrogen gas. Determine its rate law, including the rates constant with the appropriate units. So once they give us something like this and we are supposed to determine, right? If the question asks us to determine whether it's first order, it means it has limited us. If it just asks us to determine the rate constant or it asks us to determine the rate law, then we have to use our graphs. The first one we can check in no particular order, we can check whether it's a first order reaction. If there's not a first order reaction, it means we have to go on and check whether it's a second order reaction. If it's not a second order reaction, logically it should be a zero order. But we have to use graphs to check whether it's a zero order reaction. But now we are talking about just the first order. So if I have a question like this, now I'll have to draw a table of the time against the concentration, and I have to bring another column. So another column would have to be introduced where I would have the ln of the concentration of the sodium azide. Like this, right? So I would have figures for all of this, and then I will plot my graph of the ln of the sodium azide against time. Now, if I produce a straight line with a negative slope like this, it means it is first order. If I don't produce this, it means it is not first order. So that is what we have to do. Good. So we draw our table and we bring in a new column, right? These are the figures that we'll get. Now we draw the reaction, the graph. When you draw the graph, you realize that it's not a straight line, it's a curve. It means it is not a first order reaction. It's not a straight line, it's a curve. So it's not first order reaction. Now, the next one is showing us how to find whether it's a zero order reaction. We'll go down and then come back up. So second order. Now, with respect to second order, the rates, we can equate the rate equation to the second order differential rate law, and then after integrating together integral, this is what we'll get. Now, this is a very important formula for us to take note of, right? When we are comparing this to the equation of a straight line, the y is is 1 over concentration of A T is equal to KT. The KT here is the MX here. The B here is the A over A naught, right? Now the X here is the T here. It means for us to also determine graphically whether an equation, whether a process is second order, we have to plot A over AT. That's the concentration and in time T versus T, right? Versus T to determine. Now, when we get a straight line, the straight line here should get a positive slope, positive K. We have to draw a graph like this. This one will be A over concentration at T, right? This one will be time. Now we have to get a graph, a straight line with a positive slope, a straight line with a positive slope to show that it's a second order reaction. And so in the question above, let's go back to the figure above. That is what they have done. And when they have a table like this, they draw the table again and bring another column. The other column will be 1 over the concentration to give us these figures, right? The next step is that we'll draw a graph. We'll draw a graph with the 1 over the concentration versus the time. Now, if we produce a straight line with a positive graph like this, then it is a second order reaction. So it has been solved here. We can quickly go down there. like this. So I've explained this. Now, when you draw the graph, you get a straight line with a positive slope, right? Once you get a straight line with a positive slope, then you know what? It's a second order reaction. Good. Now, the next concept we are introducing ourselves to is half-life. Half-life is defined as the time required for half of reactants to react, right? Yes. And so we have ways of the using half-life, very simple. Usually half-life means the final amount or the amount at that time is half of the initial amount, right? And so if you have a graph like this, graphically, if we have initial 150, the time the reactant takes to get to 75 is half-life. So we trace the 75 to the time axis. This one, the time here will become the first half-life. Now the time we move from 75 to half of 75, which is 37.5, be the half-life again, right? So that is the graphical way of finding half-life, graphical way of determining half-life. Now, half-life means the A at T, the concentration at that time is half of the initial amount, 0.5 of the initial amount. If you put it in the equation for first order, you come and get this. So this is what you get. This is what you get. You get half-life is equal to, that's T half is equal to 0.693 over K. So if you are finding the half-life of a first order reaction, this is the formula you use. This is the formula you use to find the half-life of a first order reaction. Changes for a different order, right? So this is for a first order reaction. Now, if you are doing it for a second order, after manipulation, this is what we'll get. We'll get this. So half-life of a second order reaction, we have 1 over K, then multiplying the initial concentration, right? Multiplying the initial concentration. Very simple. So we have to also keep this to find the half-life. Usually the common one that counts is half-life of a first order reaction, right? And usually radioactive decomposition reactions are first order reactions, So that's the most common. But if you get a question that we are asked to find the half-life of a second order reaction, this is the formula we would have to use, right? Now, in all our discussion, we've not come to zero order, so quickly we have to zoom into zero order and then look at it. Now, for zero order, this is the general formula for zero order reaction, right? If you compare this one to y is equal to mx plus b, as we have been doing, it means this is y. The y is the concentration of A. The x here is this T, And so we are saying that for you to find whether a process is zero order, you have to plot the concentration of A, you have to plot the concentration of A against T. Now, when you do that plotting, you have to get a negative slope, right? Negative K. So you have to get a negative slope, a straight line with a negative slope, something like this, right? If you get something like this, that means it's a zero order reaction. It's a zero order reaction. Zero order reaction. Good. That's for that. Now, we finding its half-life, we'll put A at T equal to 0.5 of the A naught. And then this is what we'll get. So this is a formula that we have to keep, that the T half of a zero order reaction is equal to the initial concentration of the reactant over 2 times the rate constant. Very simple. Now, in summary, whatever we have talked about so far. Now, the rate law for first order reaction is equal to rate is equal to K multiplying concentration of A. If a second order, rate is equal to K multiplying concentration of A raised to the power 1, concentration of B raised to the power 1. The overall for this one is 2. Or you can have a single reactant raised to the power 2, right? As we have in this instance. Right. Right. Good. Now, for a zero order reaction, the rate is equal to the constant. So that is that for that. Now, integrated rate law, we have to keep this formula. I've already said that for first order, this is the formula that we look at. For second order, this is the formula we look at. For zero order, this is the formula that we look at. Yeah, the formula for their T halves, right, have also been listed down there. Now for plot, for us to determine whether it's first order, second order, or zero order, this is what we do. For first order, we plot the length of the concentration versus the time. Now we are supposed to get a negative slope, right? Now for second order, we plot 1 over the concentration versus the time, right? And we are supposed to get a positive slope. For zero order, we plot the concentration versus the time, and we are supposed to get a negative slope, right? That's it. That's for that. Now post test for us to try. We can try our hands on that. Then we zoom in into temperature, temperature and rate, how temperature affects rate. Generally, as temperature increases, so does the rate of reaction. We have talked about that. Now, this is because K is dependent on rate. We have also mentioned the fact that the constant depends on rate. That depends on temperature. Temperature can affect our K, right? Now we are saying that the higher the temperature, the faster the rate of a reaction, right? In many reactions, a rise in temperature of about 10 degrees Celsius causes the rate to double, right? At higher temperature, particles have more energy. That means they move faster and they are more likely to collide with other particles. When they collide, they do so with high energy. So the number of successful collisions increase, right? Now the collision model. In chemical reactions, bonds are broken and new ones are formed. Molecules can only react if they collide with each other. Furthermore, molecules must collide with the correct orientation and enough energy to cause bonds to break and form. And so the collision model is one way of describing at the microscopic level or molecular level how reactions occur. So we are seeing that reactions occur because of collision of what reactants, right? Now, during these collisions, bonds are formed and then bonds are broken, right? Now, the collision would have to collide with the right energy and the right orientation. That means they have to face each other at the right angle, and then they have to also meet at the right energy for new bonds to be formed and the old bonds to be broken. That is all about the molecular machine theory. This is a graphical representation of that theory. Now, before the reaction can proceed, we need a minimum amount of energy. That minimum amount of energy that is required for the reaction to proceed is what we call the activation energy. So we call the activation energy. Now, for different reactions, we have different activation energy, right? We are saying the rate of reaction depends on the frequency of collision and the energy of the particles, and the energy of the particles. Now, reaction coordinate diagram. This diagram actually summarizes the energy change as the reaction progresses. So if you look at the graph, we have plotted energy against the progress of reaction. Now, this is the energy of reactants. If you look here, all we have here is energy of reactants, right? Energy of reactants. Now, the energy of reactants have to increase, right? It has to rise to a certain level. Now, this rise here is the activation energy. That's the energy required to form products, right? Now, the highest point here is called the transition state. The transition state. This is a place where the reactant is being turned, right, to products. Now, at this point, there's a formation of a complex. We call the complex activated complexes, right? So at the peak here, where we achieve the activation energy, this is called the transition state. And then the complex form here, right? This is an intermediate. What we have here is an intermediate between the reactant and product. We call those complex the activated complex, right? Good. Now, when you have the product having lower energy like this means that it's an exothermic reaction. That's not really what we are talking about here. But this shows we just need you to know that the reactants need to attain a certain level of energy or the activating energy before they can reach the transition state. And then it is at the transition state, following the transition state, that we can form our product. If this energy is not provided, the reactants cannot be converted to what products. Very important to note. Very important to note. Right. So the coordinate diagram has been illustrated again here. Now, there's this very important concept we have to talk about. We call it the Maxwell-Boltzmann distribution. Two different people, Maxwell and Boltzmann, right? They independently arrive at how we can describe the behavior of gas particles, right? Gas particles. Now, after describing the behavior of these gas particles, it helped us to also look at the effect of temperature, effect of increasing temperature, right? So this is normal distribution of particles in the gas, right? So if you have something like this, this is a very simple representation. You have a container like this with gas, right? Yes, this is how the gas particles will be illustrated, right? Now, the fraction of particles has been plotted on the y-axis against the energy. Now, the energy we are talking about here is kinetic energy. Some other graphs will have speed instead of the energy there, right? Kinetic energy or the speed, right? Good. Now, the coordinate that we have to look at here is the activation energy. Is the activation energy. That's the fixed coordinate in the whole process. Now, the peak, where we have the peak here, right? Where the elements, the fraction is peaked here is the most probable energy. So this represents the energy of most of the particles. That's most of the particles would be found to have a particular energy, and then the peakedness here will show the most probable energy, right? Now, the area under the curve, the B here shows the area under the curve. The area under the curve represents the total particles in the SPC. Represent the total particles present in the gas that we are describing. The area under the curve, the total particles that we are describing. Now, the C here, the C is pointing to most particles that have energy between the two extremes. So we are looking at the fact that particles have wide distribution of energy. Some of them have very low energies, as we can see here. Now, this is the graph for energy, right? So if you are somewhere here, it means you have low energy. If you are somewhere here, you have high energy. So there's a wide distribution between two extremes, right? Some of them have very low energy and some of them have quite high energy. Sometimes enough energy to overcome the activation barrier. So that's what the C is showing us, that there's a wide distribution of what? Energy. Now the D is telling us that for a normal distribution of gas, it's only a few particles that have enough energy, right? Enough energy to cause the activation energy, hence form a product, hence transition into a product. So only a few particles, this area, the yellow area under the cave, only a few particles have enough energy to what? To cause the activation energy and probably form products, right? Now, the E here is showing us that the graph here will never touch the x-axis. The reason why I never touch the x-axis is that there's no maximum energy that we can get. There's no maximum energy. So we will not touch here so that we say that the maximum energy ends here. It's always parallel. It never touches the x-axis or the energy axis because there's no maximum energy, right? Now the F here, the F shows the average energy, So you realize that the average energy is not where the most probable energy is different from the average energy, right? Even though the most probable energy is closer to the average energy, is different, right? Different from the average energy. So this is the average energy or the mean energy of the particle. And it is not where the peak is. Very important to note. Very important. Now the G is the distribution should go through the origin because there's no molecule with no energy. So always it has to go through the origin. Now the reason why it's going to the origin is the point where both axes are zero. So where particle is zero and then energy is zero. Now we need the graph to go through the origin because it is only when we have zero particles that we have zero energy. There's no particle that has zero energy. That is what we are saying. Origin is 0, 0, right? The only way that we can have zero energy is when we have zero particle, right? Once there's a particle, there's energy. So we go through the origin to show that the only way or the only instance where we get zero energy. Because if the graph passes here, it means at zero particle, there's an energy. Or if it passes here, if the graph probably passed here, right? It means there's a fraction of particle that has zero energy. No, right? So at point, the graph always passes through the point 0, 0 to show that it is only at zero energy that we have, it's only at zero particle that we have zero energy, right? If you flip the coin, we are saying that no particle has zero energy. Now the H is pointing here. Now these to this side, right? The area under the curve to this side. Now this is the side of the particle that have the lowest energy, right? So we are saying some of the particles have very, 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 very low energy. And then sometimes it's as a result of collision. Sometimes when the molecules collide, their energies reduce or their speeds reduce. That is why we have some of them here. So some of them have extremely low energy. And this is the behavior. This is the general behavior of particles of gas, right? As determined by Maxwell and Boltzmann, as determined by Maxwell and Boltzmann. So whatever I've talked about has been explained here. Whatever I've talked about has been explained in the subsequent slides, right? Now, I said one of the practical application of Boltzmann is the distribution is that it helps us to see the effect of increasing temperature. So the T1 is normal temperature when we leave measure the gas probably at room temperature, right? Now T2 will show us when we increase the temperature when we heat. Now when we heat, this is what we see. We see the graph flattening. There's flattening of the graph, right? So the pickedness reduces. There's flattening of the graph. And then you realize that more molecules gain higher energy. So the flattening is shifting the graph to this side, right? Now, because more molecules are getting higher energy, more molecules can now cross the activation energy to form products, right? So you realize that more molecules can cross the activation energy. So this is a classical representation of the effect of temperature, right? When temperature increases, more particles have enough energy to cross the activation energy, which is the minimum energy required to form products, right? Good. Now let's read what we have down here. So we are saying temperature is defined as a measure of the average kinetic energy of molecules in a sample. Now, this is one of the most accurate, actually the most accurate definition of temperature. Right? Temperature is defined as the average kinetic energy of molecules in a sample. At any temperature, there's a wide distribution of kinetic energy, as we saw in the graph, graph, right? That's point C. Point C in the Boltzmann distribution told us that there's wide distribution of energy. Now, as the temperature increases, the curve flattens, so there's reduced in pickedness, and then it also broadens. Thus, at higher temperature, a larger population of molecules have higher energy. So that's what has been illustrated here. Now, we are saying if you use this vertical arrow to represent the activation energy, as the temperature increases, the fraction of molecules that can overcome the activation energy also increases. That is what we have observed here. That is what is being observed here, right? That if this is the activation energy, realize that with T2, when the temperature increases with T2, we realize that there's more particles crossing the activation energy. Causing the activation energy. As a result, the rate of the reaction increases. Now, stemming from the distribution, we have the fraction of molecules being calculated theoretically as exponential of EA. EA is the activation energy, and then R is the gas constant, and then the T is temperature in Kelvin, right? So the distribution was behavior of gases. So the R is the gas constant. The gas constant is a fixed value. The fixed value. Yes. So we can change this, right? That's done by Arrhenius. We can change the whole equation to connect K to the activation energy. To connect K to the activation energy. Right, and so the Arrhenius equation shows us the mathematical relation between K and then the activation energy, and it states that K is equal to A exponential of E over RT, right? Now, the E over RT, the E over RT exponential is equal to the frequency, sorry, it's equal to the F stated above here. And so we can just substitute the F into the whole equation to get K is equal to FA, right? That's a simple way of stating the whole thing. Now, the A here is frequency factor. The A in this equation is representing frequency factor. The frequency factor is a number that represents the likelihood that collision would occur with proper orientation for reaction. Right, that is it. Now, this is an expanded form of the formula that we have to keep. This is very important. We have to keep this formula, right? Now, we will compare this formula to the equation of a straight line, So we realize that we can plot the length of K, right? The length of K determined from experiment to 1 over temperature. Right now, this is a constant for a reaction. This is a constant for a reaction. Right, so 1 over T. 1 over T. Now, when we plot it like that, the slope, the M, will be equal to negative EA over R. But then the R is a constant that we know the value. R is a constant, it's the gas constant. We know the value of the gas constant. The value of the gas constant is 8.314 joules per mole per Kelvin. Right, so we know that already. And so when we find the slope of the graph, we can use that to find our EA. Right, we can use that to find our EA. Now, right after finding our EA, we can use this formula to find the K of any, the K at any other temperature. So assuming we had K1, right? K1 here. Now we can use the K1 and then the T1. With the help of this formula, we can find the EA. We can find the EA. After getting the EA, if we are asked to calculate for a different K at a different temperature, right, we can use this formula. So this is a formula for us to keep, right, because we can use this formula to find any other K, right, when the temperature is changed, whether the temperature is increased or decreased. We can use this formula. In the practical tutorial sessions, we'll learn how to use this equation better. But this is a formula that we have to keep, right? So this is a classical graph where we have plotted the length of K over 1 over T. Now, the slope of this graph can help us to find the activation energy. Once we get the activation energy, with the help of the second equation here, with the help of this equation, we can find any other K. We can find any other K at any other increased temperature. Very simple. Very simple. Now, let's introduce ourselves to effects of catalyst on reaction. Generally, catalysts would increase the rate of reaction. Now, it does that by changing the mechanism of the reaction. And so if you look at this diagram, this is the normal process of the reaction. You realize that the activation energy is quite high. Now, when the catalyst is introduced, it gives us a different path, right, with a lower activation energy, and hence increase the number of molecules that can overcome that activation energy and form products, right? Now, we are saying that in reversible reactions, the effect of catalyst on both the forward and backwards reaction is the same. It lowers the activation energy for both the forward and backwards reaction. So what it does is that it doesn't really favor the forward or backwards reaction, but it helps us to arrive at equilibrium early. That is the only thing that it will help us in a reversible reaction. Now, this one is a pictorial representation of how catalyst helps. So the catalyst is the purple background that we have here, right? So it can accommodate the reacting species, help in the breaking of bonds, and then help in the formation of bonds, right? That's quicken the breaking and the formation of bonds. So one way a catalyst can speed up reaction is by holding the reactants together and helping to break the bonds. Now, the opposite of catalyst, right? The inverse of a catalyst or the negative of a catalyst are called inhibitors, right? So what they do is that they decrease the rate of reaction. Now, how they do is that they interfere with the reactants and form stable complexes. The stable complexes require higher energy to be broken down, right? And therefore reduce the speed of the reaction. It reduce the overall progression of the reaction, right? Now, the last thing we'll talk about with respect to this particular discussion will be reaction mechanisms, right? Reaction mechanism. And if we talk about reaction mechanism, we are talking about the sequence of events that describe the actual process by which reactants become products. So for a reaction like this, A going to form B, you realize that this is the overall reaction, but it doesn't mean that A directly went to form B, right? A can go and form X, and then the two moles of the X can combine to form Y, and then 2 moles of Y can combine with A to form B, right? 2 moles of B. And so these 3 steps will actually show us how, or the individual series of steps that occurred before we could get our overall reaction, right? So this is mechanism of reaction. Now, each step within this process is called elementary reaction or elementary process. That means for this overall reaction, A reacting to form B, we have 3 elementary what? 3 elementary reactions. 3 elementary reactions. Now, what we have to note here is that the slowest step in the elementary reaction is what we call the rate determinant step. The rate determinant step is the slowest step in a series of reactions, right? In a series of reactions. Now, it is the slowest step because it requires the highest activation energy. It requires the highest activation energy. Now, under the same mechanism of action, we introduce ourselves to a concept called molecularity. Molecularity. We are saying molecularity is the total number of atoms or molecules or ions taking part in the elementary process. Right now, we are not talking about the product, we are talking about the reactants in the elementary process. And so if you look at step 1, it's only 1 mole of A, right? So the molecularity is 1. If you look at step 2, we have 2 moles of S. So the molecularity is 2, right? If we consider the step 3, we have 2 moles of Y, and then we have 1 mole of A. So we have what? 3 in total. The molecularity is 3. We don't consider the product, we consider just the reactants, the amount of atom in the reactants. Now, these are other examples for us to look at: unimolecular, bimolecular, termolecular. Now, these are important facts about molecularity that we have to note. Molecularity is always an integer. It means it's always a positive or negative whole number, right? Molecularity cannot be 0. It cannot also be a fraction. Now, we are saying that the maximum value observed is 3. The maximum value of molecularity is 3, right? Now, it can be deduced theoretically from proposed mechanism. Now, we have to, at this point, strike the difference between order of reaction and molecularity, right? Now, we are saying the order is the sum of the powers of the concentration term in the rate expression called the order, right? So the sum of, or the exponent of the concentration in the rate law, right? Or in the rate expression is what we call order. But when we talk about molecularity, I'm talking about the number of atoms, molecules, or ions taking part in the elementary reaction or elementary process. Now, order can be positive, order can be 0, it can be positive or negative, integer, or it can be fractional. Now, molecularity cannot be 0, it cannot be fractional. Now, we are saying order is determined experimentally, as we have looked at, but then molecularity can be determined theoretically by looking at the mechanism of action. Effects of pH on chemical reactions. The pH is a measure of the hydrogen ion concentration, right? And so if the pH is low, it means we are looking at a more acidic solution. If the pH is high, that is above 7, we are looking at a basic solution, right? So we are saying that in a reaction where H plus is part of the reactant, right? If we have a low pH, the low pH means that the solution is acidic. It means there's excess of H plus in that solution. The reaction will be faster in that instance. Now, in a reaction where we have OH minus as being part of the reactant, right? When we have a very high pH, that's above 7, greater than 7, what we have here is that it means the solution has excess of OH minus ions, right? And that's will be faster. That reaction will be faster. So that is how we explain the effect of pH on what? On solution. The effect of pH on solution. So we can read what we have here. We said if the reaction involves a proton or H plus, then more acidic solution will have a faster rate because the pH is really just a measure of the concentration of hydrogen ions. So if the H plus is a reactant, then a low pH will have a higher concentration than reactant, making the concentration of reactants, making the reaction faster, right? Very simple. So the same thing for OH minus ions, right? We are saying that similarly, if OH minus is a reactant, then a higher pH will make the reaction go faster because the higher pH, the concentration of OH minus is larger, right? And the concentration of H plus is smaller. Okay, so that is that for that. Now this brings us to the end of our discussion. As always, if you have any question, kindly see any member of the HESA Academic Board. Thank you very much.